Hey everyone, this is Emily. This video is all about the Central Limit Theorem, and what I want to tell you now is that the calculations associated with the Central Limit Theorem are actually pretty easy to work with. I encourage you to watch this video and then go ahead and get started with the homework for this module. However, understanding the Central Limit Theorem conceptually can take a lot of time, practice, and hearing about this information in different ways. So I've put together this video, and I encourage you to read your textbook, and then I'm going to link in the description and up in the video corner a few other videos I really liked, either when I was first learning about the Central Limit Theorem or other students have found really helpful when learning about the Central Limit Theorem, so that you can internally visualize and understand the shapes and patterns that are associated with this theorem. It's exciting. So many statistical principles are founded on this very law. So go ahead and get started with this video and then get ready to practice. Let's go. So before we talk about the Central Limit Theorem, let's review some important basics about the normal distribution. Here we have a beautiful symmetrical normal distribution. It's this bell-shaped curve, right? And we've talked about two important parameters, numerical descriptive measures. We've talked about the mean mu and the standard deviation, which we write as a lowercase sigma. Now again, mu and lowercase sigma are those statistics or parameters. Exactly, they're parameters because they are describing population details. And again, as another brief review, if we had to approximate those values using a sample, what are the two statistics that we would use? Yes, the statistics we would use are x bar and s as the mean of the sample and the standard deviation of the sample. Excellent. Fantastic. Let's get back to talking about this distribution. Let's say that our variable of interest is x. Capital X is a quantity to be measured, and it has a normal distribution. And here we designate that it has a mean of mu and then a standard deviation of lowercase sigma. When we write this with mathematical notation, we use this sentence. A normal distribution of the variable x, here we're writing it as capital X for the distribution of variable x, and see this little tilde here is this sign, and it means approximates. So the distribution of capital X, our variable, approximates capital N, a normal distribution. And then in these parentheses, we put these key details. Our mean is mu, and our standard deviation is a lowercase sigma. Excellent. And then as a reminder, we have our mu here in the center of the graph, and that stands for the mean of the population. However, it's important to remind ourselves that mu is approximately the median and the mean in a normal distribution. And if we draw a little line down the center of this graph, you can see it's symmetric on both sides, and that our most common value, our mode, is equal to the mean. And then we have this nice bell-shaped tapering off of values as we get further and further away from the mean. Next, I wanted to review standard deviation and variance. And these are two values that are related to one another, but it's important to distinguish between them. So variance, I've written it here as s caret 2, which means s squared. It's the average squared deviation of values from the mean, right? Remember, calculating variance involves squaring your deviations. Remember the distance or the difference between each value and the mean value. We would square those and then add them up. It doesn't have the same unit of measurement as the original observations. So for example, if I was working with a distribution of lengths measured in meters, m, my variance would be measured in meters squared. When I want to compare to the mean, however, I want to be comparing in the same units. So I take the square root of s squared, right? Take the square root of the variance, taking the square root of something squared. So the standard deviation is the square root of the variance. And it's the measure of what we call spread that is most commonly used in statistical practice when the mean is used to calculate central tendency. What do I mean by this word spread? I mean, if you look at a normal distribution, is it squished? Is it slender and very tall? Or is it wide and have a very long, elongated bell shape? So standard deviation helps us understand the spread around the mean. If the standard deviation is large, I would expect to see a normal distribution that's long and wide. If I have a small value for a standard deviation, I would expect to see a very tall, squished, and skinny normal distribution. And here again is a normal distribution with the useful probability values included in the area underneath the curve and above the x-axis. So again, as we've discussed, the normal distribution has two parameters, the population mean and the standard deviation. Those are numerical descriptors. And we also use this normal distribution to talk about probability of obtaining certain values in our distribution. Remember, 100% of the population scores are included in the distribution in this area underneath the curve and above the x-axis. Almost all of our probability falls within -3 and +3 standard deviations above and below the mean value. So again, a standard deviation is how we measure spread of our values from the mean. We saw the more precise percentages on the previous slide, but these three numbers are important for reminding ourselves about how probability is spread around the mean under a normal distribution curve. 68% of the values lie between -1 standard deviations and +1 standard deviations of the mean mu. 95% of the x values lie between -2 standard deviations and +2 standard deviations of the mean mu. And almost all of the values, 99.7% of the x values, lie between -3 standard deviations and +3 standard deviations of the mean mu. To work with the central limit theorem, we're going to have to build upon what we know of the law of large numbers. The law of large numbers tells us that if you take samples of larger and larger sizes from any population, that our statistic, x bar, the mean of the sample, is very likely to get closer and closer to mu, the mean of the population, which is a parameter. That means if we want to know about a population, we'll take a random sample to produce a statistic, like x bar, and we'll use that to infer about the parameter, our population mean mu. And we anticipate that if we have a larger and larger sample, if we increase the size of our sample, we'll produce a statistic that better predicts what the population mean parameter is. And this makes sense. This is why you'll often hear that a larger sample size is better in quantitative sociology, because if we have a bigger sample, we're probably better predicting the population mean by using the statistics of our larger and larger sample. The law of large numbers essentially says that probability and statistics can only predict overall results for a large number of data points or trials. And we know that this is true if we only sample 2 or 3 members of the entire United States population. We're not going to have a really strong idea of what's happening in the entire population. We want to take big samples to understand big patterns. Think about it this way. If we toss a coin thousands and thousands of times, it will probably come up heads in almost exactly 50% of the tosses. But if we toss it 3 times, it never can come up heads 50% of the time. It's mathematically impossible, right? Arguably, the law of large numbers is the most important law in the field of statistics, and lots of statistical assumptions are based on this law, including, in part, the central limit theorem. So let's learn about it. The central limit theorem is arguably the second most powerful and useful idea in all of statistics. There are 2 alternative forms of the theorem, and both alternatives are concerned with drawing finite samples in size n from a population with a known mean, mu, and a known standard deviation, lowercase sigma. The first alternative says that if we collect samples of size n with a large enough n, approximately 30 or more, we calculate each sample's mean, the average, and then we create a histogram of those means, then the resulting histogram will tend to have an approximate normal bell shape. The second alternative says that if we again collect samples of size n that are, quote, large enough, again, statisticians tend to think 30 or above is best. We calculate the sum of each sample, and then we create a histogram of those sums. Then the resulting histogram will again tend to have a normal bell shape. Generally speaking, when we're talking about changing the sample size, we want to think about the law of large numbers. When we're thinking about changing the number of samples, we'll think about the Central Limit Theorem. There are so many great videos that are out there that review the Central Limit Theorem in creative ways. And I want you to look at these videos because some students say that one method of understanding sticks more than the others. So I'm going to give you a few recommendations that I will link up here so that you can watch and better understand how the Central Limit Theorem works. The averages of samples have approximately normal distributions. As our sample size gets bigger, the distribution of our averages is going to be more normal and it will be narrower. So in this video, one of the examples they use is taking the average of cute little bunnies' weights. So if they have a small sample, just a few bunnies on a scale, and they're taking that average weight, they'll expect somewhat normal of a distribution. But as you add more and more bunnies to each sample and you take the average of each of those larger samples, and then plot those averages, the distribution will become more perfectly bell-shaped and it will become narrower, skinnier, and taller. The Central Limit Theorem is described really well in this video that I'll have you watch as well. What it's telling us is that regardless of the shape of the population distribution, look here, this frequency distribution of the population, it's not normal at all. However, if we keep taking samples of size n from this distribution, and then we plot the means of those distributions, we're going to produce a bell-shaped curve. We call this the sampling distribution of the mean. That's a technical term for what happens when we take samples from the population, take the averages of those samples, and then plot those means as a distribution. That's the sampling distribution of the mean. Let's go over an example of how this works using dice. So this example is going to cover both the law of large numbers and the Central Limit Theorem. First, let's think about the law of large numbers. When rolling a die, there are 6 different options that you can get, and we expect that there would be an equal probability of rolling any of these numbers. What's the probability of rolling a 2? Yes, about 16 to 17%. The same as rolling a 4, 16 or 17%, right? We expect the same probability of rolling each of these numbers if we rolled a die once. If we rolled a die over and over and over again, we would anticipate that the average value would be here, about 3.5. So I'll take a repeated 1 dice sample and I'll plot the results on the next slide. So here's the expected distribution of what would happen if I rolled a die an infinite amount of times. 16.7% of the time, I would expect to get a 2. 16.7% of the time, I'd expect to get a 4. I would expect to roll each number about the same frequency. In other words, I would expect that the probability of rolling each number would be exactly the same. Now, of course, even working with random chance, it's a little bit hard to meet that exact probability each time you roll. But what happens in actuality? I'm going to roll 1 die several times. What happens when I actually roll the dice? 1 time after another. It will be impossible for the first few rolls to approach this uniform expected probability, and it will take a while before the theoretical even uniform probability distribution appears. Let me show you what that looks like. As we continue to roll, this uniform probability begins to emerge as we increase our sample size. The more and more dice we roll, the increasingly uniform our graph looks, approaching the expected theoretical probability. As we keep rolling the dice over and over, our actual observed average, x bar, becomes closer and closer to the theoretical average, mu. Now let's think about how this works with the central limit theorem. Again, remember, what's the probability of rolling each number? About 17%. If we plotted those probabilities, we would know that it was supposed to be uniform distribution. It's not normally distributed at all, but when working with the central limit theorem, it does not have to be normally distributed. Our expected mean is about 3.5, but if we keep taking random samples, not all of the means are going to be exactly 3.5. What you'll see is the central limit theorem in action. The larger our sample size and the more samples that we take, the closer and closer our sampling distribution of the means will approximate a normal curve. That's the central limit theorem in action. So first, let's take a 10 dice sample, then we'll take a 20 dice sample, and then we'll repeat for a 30 dice sample. You ready to see what happens? Here's what it looks like when I roll 10 dice. I take the average of the values of these 10 dice, and then I plot the average of each one of those samples. We do have a normal distribution appear, but it has a very large spread. Now, what would we expect if there were 20 dice per sample? We would expect a taller and skinnier curve with even less spread. So instead of looking like this, we might expect something shaped more like this, a taller, more pointed normal distribution. Our spread would be reduced around the average. Now, what if I had 30 dice per sample? Now again, I would still expect that the mean of the sample means would stay approximately the same here at 3.5, but because there are more dice per sample, the spread of the sample means would be even smaller, so the graph would appear even steeper and thinner. Still symmetrical about that mean value, but taller and skinnier. Overall, the central limit theorem tells us this: as we increase the number of dice rolled, 2 to 5 to 10, or as we did from 10 to 20 to 30 dice per sample, the mean of the sample means is going to remain approximately the same. Our x bar is expected to approach the theoretical mean, mu. The spread of the sample means, however, is going to get smaller. So that means that this standard deviation is going to decrease. As n increases, the number in the sample increases, the standard deviation is going to decrease, in turn making the spread of your distribution smaller. As a result, your graph of the normal distribution is going to appear steeper and thinner or skinnier, more squished together around the mean. This is what the central limit theorem is all about. The central limit theorem tells you that as you increase the number of dice in each sample, the sample means will tend towards a normal distribution that we call the sampling distribution. Let's talk more about the formal definitions behind the central limit theorem. Again, as you remember, there are two versions of the central limit theorem. The first one is the central limit theorem for sample means, or averages. So suppose x is a random variable with a distribution that may be known or unknown. Remember, it can be literally any distribution. It doesn't have to be normally distributed. Using a subscript that matches the random variable, suppose that mu sub x is the mean of the x distribution, and the standard deviation sub x is the standard deviation of the x distribution. Now, if you draw random samples of size n, then as n increases, or as the sample size increases, the random variable capital X bar, which consists of sample means, tends to be normally distributed. And we write it this way: capital X bar, or the sampling distribution of the means, approximates a normal distribution, and the mean is the same as mu of the original x distribution. And the standard deviation you have to calculate using this formula. You take the standard deviation of the original x distribution and you divide it by the square root of your sample size. It might look confusing, but it's really simple to calculate. And what does this exactly mean? It means that if you keep drawing larger and larger samples, and you calculate the means of those sample means form their own normal distribution, and you can calculate their mean and standard deviation as follows. So consider an X distribution, which can be shaped however you want. If we take samples of larger and larger sizes from this distribution, we take very large samples throughout this distribution, and then we take the average of that sample, and then we plot it on its own histogram, and we do that again and again and again, we would see over time a normal distribution emerge. And again, no matter what the original distribution shape, the sampling distribution of the means, the capital X bar distribution, will approach a normal curve. Now let's talk about the second form of the central limit theorem, the central limit theorem for sums. Again, we're assuming that capital X is a random variable with a distribution that may be known or unknown. It can be any distribution shape. And again, suppose the same things, that mu sub x is the mean of x, and lowercase sigma sub x is the standard deviation of x. This whole sub x business, think about sub x as a little hashtag that reminds you what distribution a parameter belongs to. So if I had mu sub a, I would know to find the average of the A distribution. Or if I had lowercase sigma sub W, I know that I'd need to go find the standard deviation of the W distribution. All right, back to the CLT. If you draw random samples of size n, as n increases, as our sample sizes get larger and larger, the random variable designated as capital sigma x, or the sampling distribution of sums, tends to be normally distributed, and the sampling distribution of sums also approximates a normal curve, and the average and standard deviations are calculated as follows. Take the mu of the x distribution and multiply by the sample size. That will be the average of your sampling distribution of sums. If you want the standard deviation of the sampling distribution of the sums, take the original standard deviation of the x distribution and multiply it by the square root of n, the size of your sample. The central limit theorem for sums says that if you keep drawing larger and larger samples and taking their sums, the sums will form their own normal distribution. We call it the sampling distribution of the sums. This also approaches a normal curve as the sample size increases. The normal distribution has a mean equal to the original mean multiplied by the sample size, and a standard deviation equal to the original standard deviation multiplied by the square root of the sample size. Let's go through some examples of using the central limit theorem. Here's a reminder about how to calculate probabilities between two values. So here is one example. Let's say you were challenged to find the probability of x being greater than 7,100 but less than 7,500. This is one way to calculate it, and students have said that this is the easiest one to remember and practice the same way each and every time. So step 1, find the largest value in the inequality statement. So here, that's 7,500. Find the probability of x being 7,500 or less, so that the shading is to the left of 7,500. If you were looking at a normal distribution, you would be wanting to calculate this area to the left of 7,500. Step 2, now take the smaller value in the inequality statement. Here, it's 7,100. You want to find the probability of x being 7,100 or less, so that the shading is to the left of 7,100. So again, if I was looking at a normal distribution curve, I would be looking for this area, the area of being equal to 7,100 or less. Now step 3, take the answer from step 1 and then subtract from that the answer from step 2, like this. This is the foolproof way to calculate the probability of x lying between two numbers. And remember, you can use the Bognar app to save yourself from some z-table headaches. So let's look at this example. Is this about the central limit theorem of sums or means? An unknown distribution has a mean of 90 and a standard deviation of 15. A sample size of 80 is drawn randomly from a population. Find the probability that the sum of the 80 values, or the total of the 80 values, is more than 7,500. Find the sum that is 1.5 standard deviations above the mean of the sums. So which version of central limit theorem applies here? Exactly, sums. We're talking about the sampling distribution of sums. So we're going to find the probability that the sum of the 80 values, or the total of the 80 values, is more than 7,500. So when you're working through problems like these, you can use the handout that I've provided for this course, or our OpenStax textbook that reminds us that this is the formula that we need to use to calculate z-scores when we're dealing with the central limit theorem for sums. Let's use the information from this problem to solve it. So again, we're going to let x equal one value from the original unknown population. The probability question asks you to find a probability for the sum or total of 80 values. And now we'll say that capital sigma x equals the sum or total of 80 values. Since the mu of the original distribution is 90, the standard deviation of the original distribution x is 15, and the sample size is 80, we write the distribution as follows. The sum of x approximates a normal distribution, and we calculate the mean by multiplying 80 by 90, and we calculate the standard deviation by taking the square root of our sample size 80 and multiplying it by 15, the standard deviation of the original distribution. Let's break that out. What's the mean of the sums? Again, we're taking our sample size, 80, and we're taking our original mean, which was 90. We're multiplying those two together, so we're expecting an average or a mean of 7,200. Now, what's the standard deviation of the sums? Again, we just use the given calculations. We're going to take the square root of the size of our sample, 80. We're going to multiply it by our standard deviation, which was 15. 8.94 times 15, 134.1. And now we go to use the Bogner applet. In the mu box, we plug in 7,200. That's our calculated mean of the sums. Here, we plug in the standard deviation of the sums, which we calculated here, 134.1. The x value that we're given is 7,500 here. So we plug that into the x equals this blue box. And now remember, the problem is asking whether the sum of 80 values is greater than or equal to 7,500. So we make sure to select this drop-down option, and we're going to check it by looking at our graph. So we select this drop-down option and we click away, and when we do, this small area is shaded, and it makes sense. We're looking for the probability, the area under the curve, greater than or equal to 7,500. And as you can see, we get this answer, about 1.264%. Excellent job. Let's go through another example. Let's read through the problem. The length of time in hours that it takes a, quote, over 40, unquote, group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. A sample size of n equals 50 is drawn randomly from the population. Find the probability that the sample mean is between 1.8 hours and 2.3 hours. All right, let's pull out the information we need and then decide what form of the central limit theorem we're supposed to use. All right, we're going to say x is the length of time in hours, and then it looks like our mean mu of x equals 2 hours, and our standard deviation of x equals 0.5 hours. Now we're finding the probability that the sample mean is between 1.8 and 2.3 hours. So which CLT will we use? Exactly, the central limit theorem of means. As a reminder, this is the information from our introductory statistics OpenStax textbook about how to work with the central limit theorem of means. So again, we have the x equals the time in hours it takes to play one soccer match, and the probability question asks you to find a probability for the sample mean time in hours it takes to play one soccer match. Capital X bar is the mean time in hours it takes to play one soccer match when we take a sample of all of these different matches that are played. So if mu of x equals 2, and the standard deviation of x is 0.5, and n equals 50, then we know that the sampling distribution of the means, or capital X bar, approximates a normal distribution that is also going to have a mean of 2 and a standard deviation that we have to calculate. We take the standard deviation of x, 0.5, and then we want to divide it by the square root of n, and that was 50. N equals 50. So we divide it by the square root of 50, and that approximately equals 0.07. Great, we have all the values we need. So we're going to go to the Bogner applet, and we'll enter our mu of means, which is going to equal our original mu of x. So we enter that here as 2. We enter our standard deviation of means, which is 0.07, and then we're going to have to calculate this twice. The first time we're going to take our largest value, 2.3, and we're going to find the probability of being less than 2.3. Being less than 2.3 is 0.9999999, and you can see here's about 2.3, and this is the shaded area underneath the curve to the left of it. And now we want to find the probability of being less than our lower value, 1.8. So we enter the same mu and standard deviation, but we enter 1.8 as x. And I know it's hard to see, but right here is all that shaded area to the left of 1.8, which is 0.002. So 0.999 minus 0.002, our probability of an average game lasting between 1.8 and 2.3 hours is 0.997. So the probability of our sample mean being between 1.8 and 2.3 is about 99.7%. Let's go through a few quick questions to make sure that we understand the basics of the central limit theorem of means. A, when the sample size is large, the mean of the sampling distribution of the means is approximately equal to the mean of x. Does mu of x approximately equal mu of x bar? Yes. When the sample size gets larger and larger and larger, the mean of the sampling distribution of means is approximately equal to the mean of the original distribution. B, when the sample size is large, the sampling distribution of the means, capital X bar, is approximately normally distributed. Is that true? Yes. Look down here at the information from our textbook. The sampling distribution of our means, capital X bar, approximates a normal distribution. Let's look at number 3. When the sample size is large, the standard deviation of capital X bar, the sampling distribution of our means, is approximately the same as the standard deviation of x. This is false. Let me show you why. The standard deviation of the original distribution is written as follows. The standard deviation of the sampling distribution of means is that exact value divided by the square root of n. And as the sample size gets larger and larger, this denominator will get larger and larger. So the standard deviation of the sampling distribution of means is actually smaller than the standard deviation of the original distribution. And as the sample size gets larger and larger, the standard deviation of the sampling distribution will get smaller and smaller. Let's review this final piece about the central limit theorem of sums. Which of the following is not true about the theoretical distribution of sums? Are the mean, median, and mode all equal? Yes, the theoretical sampling distribution of the sums approximates a normal curve. And by definition, the mean and median and mode are all equal in a normal distribution. The area under the curve is 1. Yes, again, because it is a normal distribution, the probability area under the curve is always 100%, or 1. The curve never touches the x-axis. Yes, again, this is true just by the definition of the shape of the normal distribution. It's always above the x-axis. D, the curve is skewed to the right. No, normal distributions don't have any skew. Thanks for tuning in, and I will catch you next time.